All right, everybody, I'm going to call this Unit 1.2, meaning it's the second small portion of our first unit of chemistry. So where we left off was the states of matter. I know you guys know this is nothing new to you, but it's something we do need to cover. As you guys know, a solid, such as my cell phone here, has a definite shape, a definite volume. It is hard, nothing new there, right? A liquid, of course, has an indefinite shape, meaning it will take the shape of whatever container it is in, except it'll be towards the bottom because, of course, gravity is going to keep it down. And it has a definite volume. It cannot be compressed. It's going to have a definite volume, but the shape of it can change depending on the container that it's put in. A gas or gaseous is going to have an indefinite shape and an indefinite volume. It could be as large and expand to as big a volume as you want, or it could be compressed into a very small amount of space, which of course is how a lot of hydraulics and things like that work. Is you're able to compress and create a great amount of force to do work. So they can be squeezed and they can be expanded, and it will take literally whatever shape, not just the bottom like the liquid, but literally the entire volume of whatever container that gas may be in. Now, what may be new to you is the word aqueous. Aqueous refers to something that is dissolved in water, specifically water. In chemistry, we put that in little parentheses with in italics AQ. So aqueous means it is dissolved in water. That is different than, say, a liquid. A liquid is literally any liquid, whereas aqueous is something that is dissolved specifically in water. The next one, of course, is plasma. We're not really going to touch on this, but again, it is one of the states of matter. It's a very, very high energy, very rare. The only time you ever really see it, of course, is lightning. And also whenever a spaceship is coming or a spacecraft is coming back into the orbit of or back into the atmosphere of Earth, there's a huge amount of red fire and yellow. That is plasma because it is superheating the atmosphere as that spacecraft enters into our increasingly thick atmosphere as it comes closer to the surface. But like I said, you and I, other than lightning, we don't ever experience plasma on a daily basis. Those are the 5 states of matter that we're going to use. Like I said, really just the top 4. So you need to be aware of those. When we do a chemical equation, again, if we put a parentheses with an S, that means solid, parentheses with an L, liquid, parentheses G, gas, and parentheses AQ for aqueous. And just to repeat, that is not a liquid, that is something like a solid dissolved into water. All right, so changes in state. Starting with the ones that you may not be aware of, there's something called sublimation. Sublimation is where a solid skips the liquid phase and goes directly up to a gas. The best example I could think of is like dry ice. Dry ice, again, is very, very cold. It is a solid form of carbon dioxide, and you could put dry ice literally on a piece of paper, and the paper does not get wet. And that is because, again, it's in the solid form, and then you guys all know like the crazy vapor that's coming off of the block of dry ice. That, again, is it's going from a solid state directly to the gaseous state and skipping the liquid state. It's very rare. Other than dry ice, I have a really hard time thinking of another specific example of that, but that is called sublimation. Please don't forget that one. We're not going to use it a lot, but it's just one that we don't encounter on a daily basis, so it's kind of easy to forget what that term means. Deposition is kind of the opposite. It's where you're going from a gas all the way to a solid. This is very difficult to do. Again, you and I in our kitchens or in a typical laboratory do not perform deposition, but that would involve intense amount of pressure, and you are basically squeezing the molecules into a very small ordered state, which would be a solid. So those are the opposite. Sublimation, solid to gas, gas back to solids, both of them skipping the liquid state is called deposition. You guys all know melting, solid to liquid, freezing, liquid to solid. Those two, again, are opposites. They're just going in different directions, but the exact same thing is occurring on the molecular scale. Vaporization, basically we also sometimes call it evaporating. Vaporization is from a liquid to a gas. Of course, like say you're boiling water, that's vaporizing. The liquid water is boiling up into the gaseous state. And then condensation is the opposite of that, where the gas condenses into a liquid. So again, sublimation, deposition are opposites, and again, they're unique because they skip the liquid phase. Melting and freezing are the exact opposites. Again, we are very familiar with those on a daily basis. Vaporization and condensation, again, are also opposites. So please make sure you guys know those. All right, getting a little bit more interesting stuff. We need to know basically about what a chemical property is and a chemical change versus a physical change. So a chemical property is the ability of a substance to undergo a fundamental change that literally changes the substance that it is. One of the best and easiest examples to give you is like, say, you burn wood. Wood is, again, a solid made mostly of a lot of carbon and cellulose. When you light it on fire and it burns, what you're left with is a whole lot of gas and a whole lot of ash. The wood is gone. You cannot get the wood back from the gas, the heat, and the ash. That is a chemical change, okay? That is an example of a chemical property of wood, okay? Chemical properties, again, are the ability to undergo a change. A chemical change, I'm going to go over it again in just a second, is it's changing fundamentally the substance that it is on a chemical level. All right, so that's that there at the bottom. Again, it says a process involving a change in one or more substances. Let me shrink that for you guys so you can see that a little bit better. Involving one or more substances changing into a new substance, that's also called, of course, a chemical reaction. A firework, if you launch a firework, it's not going to come down as the pre-packaged firework. It's going to come down in tatters and a whole lot of light and a whole lot of heat and hopefully a nice big bang. That's a chemical change. A physical change, on the other hand, is really, really different. You may change the shape, you may change the size, you may change some sort of thing, but fundamentally it's still the same thing. A really good example is taking a pencil and breaking a pencil. When you break a pencil, is it a completely different thing? No, of course not. It's a pencil. You just broke it into two pieces, right? It's still a pencil. You can still use it to write. You can still use it to erase if you have both ends, but now it's just cut in half. That is totally different, say, than burning the pencil with fire. When you're done, you're going to be left with ash, heat, light, and gases. You can't get it back. So that's the difference between a physical change and a chemical change. Again, in middle school, you study a lot of physical changes. We're going to obviously study mostly on the chemical changes and how things fundamentally change their substance. Okay, so there are a few indicators that you guys need to be aware of a chemical change. If you see any of these, not a collection of them, but even just one of them, that is an indicator that a chemical change has occurred. Some of these are fairly obvious. Like, for example, I'm going to start at the bottom. If it changes smell, for example, if you have milk in the fridge and you don't open it for a while and you forget it's there and you open it and you smell it, you're like, whoa, that's rancid. That is a sign that the milk is curdling and is going bad. There's a chemical change going on. And again, you cannot get that curdled, chunky, gross milk back into a nice, smooth, fresh milk. A chemical change is happening. It's a one-way process and it cannot be reversed. Another is a change in color. If something is changing in color by itself, and I don't mean painting walls like I did over before school started, but I mean literally it changes color by itself. Think of like a banana going from a nice yellow to a brown. Again, that's a one-way process. You cannot return it back to a yellow banana. That is a sign of a rotting chemical change. If light is released by itself, say, again, like a firecracker, right? That's another good example. You launch it up, it's a solid thing, and then explodes. Massive amount of heat, massive amounts of light are released. Again, that is a sign of a chemical change. Now, going again from the bottom, a precipitate is basically where you mix two liquids and a solid forms. Two liquids, a liquid mixed with a liquid, and at the bottom, a solid is created. That is a precipitate. Again, the solid was not there. The solid is now there. Once you form the solid, you cannot return it back to its two liquid states. Therefore, that is a sign of a chemical change. Finally, of course, bubbles. Now, I don't mean like, say, if you open a can of soda and all of a sudden bubbles come out. That is not a chemical change. They pressurized and put carbon dioxide in the can, and they pushed it in there with pressure, capped it, and then when I open it, you hear the psht, and of course the gas slowly starts to release. That's not a chemical change. That is a physical change. There was gas dissolved and is now coming out. Fundamentally, it's still the gas, and it's still the syrup, and so on. There's not really a chemical change there. What I mean is, if gases are produced by themselves, you mix something, you do something, and all of a sudden, bubbles are released. A really good example is the good old elementary volcano. You mix baking soda, vinegar, again, one's a powder, one's a liquid, you mix them, and voila, you get bubbles. That's a chemical change. Again, if you see any one of those six, then you know a chemical change has occurred, which again is fundamentally different from a physical change. Just to repeat, a physical change is something that does not alter what it is. You may not be able to return it. For example, if I cut a piece of paper in half, no, I cannot put it back together, but it's still paper. I didn't really do anything. I just made it into two smaller pieces, okay? That's the big difference there. Again, so if you are asked, is this an example of a physical change or is this an example of a chemical change? Just ask yourself the very simple question, A, is it fundamentally the same thing, or has it created and made something new that was not there before? And could I take that and return it back to its original state? If you can answer those, then that will again tell you whether it's a chemical or a physical change. All right, so to finish up this 1.2 video, I'm calling it, let me just finish really quick with something called the Law of Conservation of Mass. You guys have heard about this in middle school. Again, it is a law. And therefore, it's true even in every example you could think of. Mass on Earth is conserved. There is a fixed amount of mass on the planet Earth. It is recycled, it is changed, it is moved, but it is not created, nor is it destroyed. It is the same mass that has been there since the very first creation of our planet, and it's the same mass that will be there till the very, end of our planet. It just gets recycled and changed. So mass cannot be created. It cannot be destroyed. It is, again, like the name implies, conserved. So you guys have probably heard of how we balance the chemical equations. You guys may have seen that process. Again, the whole reason why we have to balance chemical equations is because the product side always has to equal the reactant side, because it's all still there. It may look different. It may have turned into a gas. It may have turned into, I don't know, a liquid or something, but it's still all there somewhere. It may have escaped to the atmosphere and the environment, but if we were able to capture it, it would still be all there. So here's a very simple example. It says we have 216 grams of mercury 2 oxide is heated and decomposes, which means to break apart into mercury and oxide, into oxygen and mercury, like I just said. So 200 grams of mercury is collected, so therefore what is the mass of oxygen, which is a gas, that would have escaped to the atmosphere? The mercury, of course, would be left as a liquid at room temperature, and then we would be left with less mass now, and then gaseous oxygen, which would escape into the air of our room. So a very simple question is how much gas must have been released of oxygen? Again, it's pretty simple. You just take the mass before, which is 216 grams, the mass after, which is 200 grams. Where's the difference? That obviously is 16 grams. Therefore, we must have let escape 16 grams of oxygen. That, again, is just a very simple example of the law of conservation of mass. It's always there. Like I said, you may not see it. For example, just to finish this up really quickly, if you burn a piece of wood, yes, the wood may look solid, it may look big, and when you're done, you have just a sprinkling of ashes that's very lightweight, and there's not much there, right? You're thinking, well, there's no way that can be conserved. Keep in mind, the vast majority of it escaped into the gaseous forms of carbon dioxide, water, and decomposed cellulose. So it's all there, but like I said, we just don't capture it. If we did, we could still weigh it, and it would equal the exact same mass as the log before we burned it. So that's called the law of conservation of mass, okay? Again, thanks for watching. If you guys have any questions, please ask.